Let's take a look at example 8. Let h be a function having derivatives of all orders for x. Selected values of h and its first four derivatives are given in the table below. All right, it's a tabular question. We've definitely seen these question types before. They're fairly popular on the AP exam. And, in the context of some other FRQs that we've seen, we had to do stuff like Riemann sums. Maybe we had to approximate the derivative. And here we're seeing it for the first time in the context of a series, we assume. All right, let's take a look here. The function h and these four derivatives are decreasing on the interval from 0 to 2. I'm thinking that's going to come up. Whenever it tells us our function is decreasing, our derivatives are decreasing, it is an important piece of information. Who knows? Maybe it's about concavity. Maybe it's about over or under approximating either a Riemann sum or, let's say, a tangent line. Right. Okay. So let's take a look at part A. Right, the first degree Taylor polynomial for h about x equals 1 and use it to approximate h of 0.9. Does your answer over or under approximate that value? There you go. Over, under, approximating, and explaining your answer. So first up, we have a first degree Taylor polynomial, which means we are writing essentially just a tangent line. That's easy. All right, and then how is it that we're going to be able to determine whether or not we over or under approximate our answer? It's about concavity. Concavity. Now I'm going to reiterate this. Every single time it comes up on a test or a quiz question, everybody wants to talk about the concavity specifically at this point, but that's not what you do. Remember, you need concavity on an interval. The reason why is because your graph could do something else, either right here at 1 or beyond 1, in between 1 and point H or something like that. We have to make sure that it behaves. It keeps doing that thing that we expected it to do. In other words, keep its concavity. So you know what? This one's pretty straightforward because it gives us the interval that we're talking about here that we need to use. All right, that's fantastic. So let's go ahead and start our first degree Taylor polynomial or tangent line, part A here. I'm going to label this as a t sub 1 of x is equal to, so we start with our y value from our table. Let's see, at 1, our h value is a -2, easy enough, plus, now we need our slope, and we're going to multiply that times x minus 1. So our slope is going to be at h prime, it's a -5. Oop, eraser, boop. -5 times x minus 1. That was easy. All right, hopefully the rest of it is just as easy. Now we have to use our tangent line to approximate h of 0.9. So we just plug that in. -2 minus 5, 0.9 minus 1, and this is free response, so you're more than welcome to stop right there. I think I'm going to go ahead and keep going, though. -2, I love arithmetic. In the parentheses here, we would have a -0.1, which essentially just moves this decimal place over 1, and then we cancel out our signs. So we've got a -2 plus 0.5, which gives us a -1.5, meaning that we are approximating h of 0.9 to be about -1.9. So I am imagining that if this was a real free response question, then that would have been worth a point, and this one would be worth a point, and then your final point is the over or under approximation thing. Okay, so we need to figure out what the concavity of our shape is around both 1 and 0.9. And that concavity is dependent upon the second derivative. So if you look at your values of your second derivative, they're all negative, but that doesn't make a difference. What does make a difference is the fact that it and all of these other values are decreasing. If your second derivative is decreasing, then your shape must be, your curve must be concave down. So I'm going to write that. Since h double prime of x is decreasing, And where's it decreasing? Oh, it's decreasing at this point. Not good enough. Oh, it's decreasing at this point. Not good enough. On the closed interval from 0 to 2, that's a weird looking 2. That's better. Let's see, h of x, that looks like an f, now it looks like an h, is concave down on this interval. Doop. And let me just kind of sketch a little picture here. So we got concave down, and then we have our tangent line, and we can see that our tangent line is going to be up above, and we're going to be over approximating the value of our function. Is concave down. Here, I'll just put an and. The tangent line or maybe I even say the first degree Taylor polynomial. This is extra. The fifth degree. First, good thing it's not a spelling test. The first degree Taylor polynomial. That's an M right there, not a double N. Over approximates the value of the function. In other words, we would have, this is negative 1.5 has to be bigger than the actual value of h of 0.9. And of course, you can flip that inequality around or whatever. All right, so that's probably worth the last point on this one. Okay, so part B, let's see what it says. Write the third degree Taylor polynomial, and we're going to use it to approximate h of 0.9 once again. Alrighty, so we should get a little bit more accuracy here. Part B, we want the third degree. And you know what? We're part of the way already there, starting with a y value, minus 5 times x minus 1. All right, so there's first degree, same thing as the tangent line, and now we need the second derivative at 1, which is a negative 8. So minus 8 over, this one's over essentially a 0 factorial, don't need it. Over a 1 factorial, also don't need it. Over a 2 factorial, yes, I do need it. And then x minus 1 squared. And now we just need one more term. And let's see, we've got negative 18 at the third derivative. Minus 18. Where's the pen go at? 18 over a 3 factorial times x minus 1 cubed. Fantastic. All right, so I might go ahead and clean this up just a little bit. It's not necessary, honestly. 8 over 2 factorial is just 2, so I replace that with a 4. And then 3 factorial is 3 times 2, which is a 6, and 18 divided by 6 is a 3. Oh, that's lovely. And then the last part, we don't have to do an over or an under approximation. All of that is just based on like a tangent line approximation, or maybe even, what else do we do it on? We also do it on Euler's method, but that's also tangent lines anyway. So t sub 3 of 0.9 is equal to negative 2 minus 5. And whenever I go to stick in 0.9, it's going to be the same thing that I got right here. It's going to end up being a negative 0.1 on each one of these. So I'll just write that in here. Minus 4 times negative 0.1 squared minus 3 negative 0.1 cubed. And under no circumstances would I recommend working that thing out by hand. I'll just box that answer and be done with it. For sure, unless this is a calculator active question, but I have a feeling that it wouldn't be. All right, so that means that one's done, and we have one final part, and I have a bad feeling about this. It says part B again, which I'm pretty sure C comes after B most of the time. Use the Lagrange error bound to show that the third degree Taylor polynomial for h about x equals 1 approximates h of 0.9 with error less than 2 times 10 to the negative fourth. Fantastic. So here, let's talk about Lagrange again. And it has to do with the error, the remainder. That remainder here, and let's see, we used third degree, right? So if I take the absolute value of that, I'm going to associate this with the next term. So we went up to the third term, so now we're going to look at the fourth term in order to determine how far off we could possibly be. So the absolute value of the remainder, all the stuff that's left over, is less than or equal to the absolute value of, and then you're going to look at the next derivative. So here, this is going to be the fourth derivative. I put in f, but it's an h. And then it's evaluated at some value, which I'll call z. And remember that z is going to be between, it's going to be between our 1, our center point, and 0.9, where it was that we evaluated our function at. And it's the value that maximizes that fourth derivative, or the absolute value of that anyway, over a 4 factorial, and then we're going to multiply that times our x minus 1 to the fourth. Okay, so when I stick in my 0.9 here, I'll stick in my 0.9. I know that this part is just going to simplify to that negative 0.1 here. Go ahead and put that in there. And now I have to figure out, what am I going to do about this guy? So essentially here, we need to get the max value on this. And it's the max value of the fourth derivative, the absolute value of that. And since we don't have a graph, and since we don't have a function in order to be able to do that, we need to use the table values. And we have the fourth derivative in our table values right there, right? And notice that they're negative, and that's kind of important. They're both negative and they are decreasing. So let me kind of sketch a little picture of what is going on here. So you have here, let's change some colors. So let's put in this graph grid like so. So we have our function, which is both negative. It's going to start down below the x-axis, and it's going to be decreasing. But we need to take the absolute value of that thing. And when we take the absolute value of that, it's going to flip that guy up above. So really, this is the graph that we're going to look at. Okay, and let's say, for example, if I put some numbers on here, let's say this is the number 1, and then we would also have the number 0.9. And if I look at my increasing graph, it's now increasing, of course, because it reflected over the x-axis. We can see that the higher value is going to occur at 1. And so that's the value that's going to maximize our derivative. Max h4 of x. And remember, on these kind of things, technically this is like an optimization problem where you're trying to optimize that derivative, and sometimes that's just way too hard, so we just find a very convenient value here, and that convenient value is going to be at 1, and we get that value from the table. At 1, it says negative 144 over 5. So that's the number that we're going to plug in here. Oh my gosh. All right, so I'm going to rewrite some stuff. And this is going to be less than or equal to 3 absolute value, negative 144 over 5 over 4 factorial, which was, I think it's just 24. And then we have times 10 to the, actually, let's say it's not 10. What am I doing? Actually, it is going to be 10, right? So this is essentially a negative 0.1, which is negative 1/10. And we're going to raise that to the 4th power. We don't have to worry about the negative sign because we're raising it to the 4th and we're taking the absolute value. And then I can think of this as basically 1 over 10 to the fourth, which is the same thing as 10 to the negative fourth. So I'm going to write it kind of in scientific notation. All right, now then, what we want to do is just basically try to simplify this, because remember, we have a number that we have to show that it is less than. Where the heck did it go? It's all the way, way down here. It's got to be less than this guy. So I do have to do a little bit of arithmetic to try to fix this thing. So the negative is going to be gone. I have 144 divided by 5 that we're going to divide by 24, which is the same thing as multiplying by 1 over 24. All right, I do know for facts that 12 goes into both of these, right? So this is 144 divided by 12 is going to go in there 12 times, and then this goes in here exactly 2 times. Oh, but that means 24 could have gone in there. So if I divide the 2 in there, we get a 6. All right, so what value do we have so far? So far we have 6/5 multiplied times 10 to the negative 4. 6/5 is 1 point, let's see, there's going to be 1 left over. That's 1.2 times 10 to the negative 4. And we are in business because that is less than 2 times 10 to the negative 4. Absolutely fantastic. All right, so that concludes the Lagrange error bound on this free response question where we had, let's see, what did we have? We had a first order, first degree Taylor polynomial. We had a table of values, which made this problem rather unique. And it did say something about it being decreasing, so we had to make sure that we took that into account. It had to do with some concavity. And you know what? Let me go ahead and take this opportunity to repeat the fact that, hey, concavity on an interval whenever we're doing this over or under approximating. Done.